Thank you so much, Nanshu, and also Jia for the invitation. It's an honor to be here. And also great to kind of start off the day after a really wonderful talk by Stephanie LaCour. So kind of a hard act to follow, but I'll do my best here. So, as Nanshu mentioned, my group, we do kind of work in areas kind of related to soft materials engineering. Some work on soft machining, soft robotics, but for today, I'm going to focus on our work on kind of more printed soft electronics, and later I'll talk a little bit about applications in bioelectronics. First, I want to acknowledge the people who actually did the work. I'm here merely as a spokesperson. It's a fairly diverse and interdisciplinary group, people coming from a variety of different backgrounds, scientific disciplines. So it's really been fun and a very dynamic group in the sense that most of the folks actually in this picture have kind of moved on, and we have new folks coming in. So the constant flow of really talented researchers here. I also want to acknowledge I'm going to spend quite a bit talking about some of the collaborative work I've been doing with a lab over in the University of Coimbra in Portugal. So this is a group led by a faculty faculty, and we've been working with them through this joint CMU Portugal program. So a lot of what I'm going to show is actually through co-advised students through that partnership. Right, so I'll just kind of jump right to it. The theme of this conference, of course, flexible, soft, printed electronics and sensors, and there's all sorts of different material architectures to achieve that. And my work has done quite a lot in this top right quadrant with liquid metal, and then there's a lot of kind of nice advantages to kind of to that exploit kind of their high electrical conductivity, but also their kind of low viscosity and their kind of fluid-like rheology. But of course, we talk bioelectronics. I mean, the gold standard is, of course, all the amazing work that's being done with hydrogels and organogels, and so that kind of also represents a really big thrust. In the bottom left here quadrant, there's all sorts of work with nanomaterials, everything from kind of intrinsically functional polymers and elastomers to just basically simple binary compositions of taking, say, like gold nanoparticles or silver flakes, just mixing them into rubber and getting functional properties that way. Let's say kind of of all these, perhaps the most important is actually what you see in the top left quadrant. That kind of relates to a lot of what you saw this morning and then Stephanie's talk on these kind of so-called deterministic architectures. So Stephanie is, of course, one of the leading pioneers, going back to even her days back at Princeton, leading a lot of the research on kind of these ultra-thin film radio electronics. So we have Nanshu Liu, of course, here also kind of a pioneering researcher in the space who kind of looks at this not just from the functional perspective, but also from the underlying kind of mechanics and principles of the science of these systems. And of course, you have John Rogers and plenty of others kind of working in the space as well. So that's kind of a feel that kind of beyond just stretchable electronics in terms of connectivity and circuitry, but also achieving other types of functionalities through thin film semiconductors and other other functions. So I'm largely going to focus on work on liquid metal because I do think, at least within the domain of printed soft electronics, that these kind of stand out as particularly promising. So we are not going to achieve all the same functionalities that you can get with those wavy and serpentine deterministic architectures, but you do have the advantage of this kind of ability to rapidly produce circuits at large scales using these kind of direct and bright printing techniques. So that's where I'll kind of focus this work. I'll start just by talking about some of what we've discovered with liquid metal, which is a particularly versatile material for this. We use a eutectic blend of gallium and indium, so two metals that are solid at room temperature, but when you mix these together, you form this eutectic that's liquid, and depending on the size of the liquid metal in the form of microfluidic channels or microscopic or nanoscopic droplets, you can get this alloy to remain liquid even down to very low temperatures, down to as low as -70, -80 degrees C. So you can see on this is just kind of one image from a review paper from a few years back, just showing all the different types of ways that you can incorporate liquid metal into kind of soft off substrates to achieve all sorts of different functionalities. There's a lot of research groups throughout the world kind of working on this. This has been a kind of a popular research for well over a decade now. I have to actually credit my colleagues, Michael Dickey, George Whitesides, Ryan Sheshi, who really kind of basically reintroduced the engineering community to a lot of these liquid metal architectures. But really this concept of using room temperature liquid metals really goes back decades, even back to the 1940s and 1950s. So in some ways, there's not really much new. As with a lot of kind of areas in kind of academia, there's this kind of a cyclical pattern of kind of, rediscovery. With each kind of iteration, there's some important steps that have been made. And now I feel kind of there's been this breakthrough where that we found much more versatile techniques for processing and patterning these materials so they can be used in a wider range of electronics applications. Now, one of the challenges, though, and this kind of was something alluded to by Stephanie LaCour in her plenary talk, is that these liquid metals actually are kind of still a little bit difficult to kind of process, at least with methods that are compatible with kind of more standard microelectronics and PCB manufacturing. So early on, kind of working with these materials, a lot of my efforts were actually focused on taking some of the traditional PCB patterning and rapid prototyping tools, and then trying to apply that to liquid metal to create these soft and stretchable digital electronics. And so we've found that probably the most kind of reliable and best approach, at least for us, is to use UV laser micromachining. So we just use an LPKF proto laser. Basically, it's something that's intended for PCB prototyping, and then just applying it to liquid metal. The key here is that we deposit the liquid metal not directly on a soft rubber substrate, but instead we have this really thin film, kind of nanometer thin film of metal. You typically chromium and copper. You could also use gold. And then depositing liquid metal on top of that, and then using this laser ablation technique to create your circuits. And what's funny is that the liquid metal not just functions as these soft, kind of stretchable fluidic interconnects, but they also double as your solder. And so you can use this kind of reducing method, just like you would with a flux and kind of more traditional soldering to mount your electronic chips, and then you can make these fully functional digital circuits that can still interface with virtually any kind of packaged IC. In this case, we have quad flat pins, but this really works with Goldwing and ball grid and pretty much everything else. Here's this kind of another recent example. This is actually a really exciting collaboration with Professor Tyler King, who's here in the back. And this was work done by a really phenomenal master's student. I guess she's part of this master's PhD, where she basically applied that manufacturing method of having liquid metal on in this case, a gold film on and then also did these kirigami cuts to get even more stretchability and compliance out of these systems. So again, quite versatile. The key is, unlike what I kind of, claimed in the very beginning of this talk, is that we don't have this printability, right? This still kind of requires this kind of subtractive ablative technique. Yes, it's compatible with kind of rigid PCB manufacturing, but it's not quite what we want for really kind of mass scale production, right? So these approaches, while nice, and good for kind of these kind of low volume type implementations, really kind of fall short of what we need kind of longer term. So that kind of led us to looking at a different architecture for blending the liquid metal and elastomers, and that's in the form of these suspensions of micro and nanoscale droplets. We call these liquid metal embedded elastomers. So you have these metallic inclusions. They're liquid, so they can kind of stretch into form with the surrounding but they're metal, and so they can endow these materials with very high, either high electrical conductivity or high thermal conductivity. Now, to achieve high electrical conductivity, we have to have really large concentrations of these droplets. So, on the order of 50% by volume, or, 85, 90% by weight. And then also to get these droplets to kind of connect, we have to do this so-called mechanical sintering process, which is a little bit messy. And some of you, who've had experience with this, like Watson, we've kind of worked together, on creating these kind of stretchable, RF type devices. It looks kind of clean here where we use this Cricut pen plotter, but if in practice, sometimes you just have to apply really intense pressure to get those liquid metal droplets to rupture and connect with their neighbors. So not really kind of the best thing. But when you do get a percolating network of these droplets, you get something that's quite conductive and also quite stretchable. What's not captured in this video here, I'll run again, is that one nice feature of the microstructure of these LMEE composites is that their electric resistance is actually quite stable, even under really extreme strains. You can stretch these to 500% strain, 600% strain, right? So, 6-7 times their natural length, and you see virtually no change in electrical resistance. You still are able to maintain, say, 1 ohm or half a ohm. And then, with Watson, we also kind of explore the impact on kind of the impedance, kind of not just DC, but also AC at very high frequencies, just to kind of see what the response to deformation is there. So, promising, but still kind of messy. And again, not printable, right? I mean, you ultimately need this mechanical sintering approach to creating the types of circuits you need for digital electronics. And so, basically, we kind of took a step back and working with our collaborators at Carmel in Portugal. So this is Mahmoud Tavakoli's group. We thought, okay, let's not be so dogmatic with using just liquid metal in elastomer, and let's just kind of try to incorporate what's traditionally used in print electronics and start working with some of these nanomaterials. And in particular, just taking some of these silver nanoparticles, silver microflakes, and then blending that with the rubber and the liquid metal. So it's well known, of course, that if you just take the silver, by itself and blend it with PDMS, you can achieve very high electrical conductivities. Again, it requires very high volume fractions, very high weight percents. In the case of just silver alone as a filler, as a lot of you probably have experienced, these high weight percents also make these materials quite brittle. And when you start stretching the materials, you start degrading that percolating network, and you lose electrical conductivity. So good for flexible circuits, but not really great if you want very robust, highly stretchable electronics. So the solution is to again kind of start working with the liquid metal. This is actually a kind of approach that is not builds off of something else that Stephanie LaCour had pioneered that she didn't get a chance to talk about in this morning's presentation, and that are these so-called biphasic architectures, where again she has the liquid kind of interfacing with in her case gold, having that kind of on a rubber substrate, and not too unlike kind of what I showed earlier with our laser patterned electronics. What we're proposing is a very different type of biphasic architecture. And by biphasic, I just mean that there's kind of a liquid phase with our eutectic gallium medium, but then also the solid phase with these silver flakes. And then having that all blended in and embedded within this kind of rubbery dispersion medium. So now we actually have something that's printable. That doesn't require any mechanical sintering because basically those silver flakes kind of form the bridges between the liquid metal droplets. We don't have to apply intense pressure to rupture the droplets to get them to connect. Unlike kind of just silver flakes and polymer alone, we have kind of a fairly low concentration of these rigid filler particles, so we can kind of maintain a pretty low viscosity, and then in the cured state we can have something that's quite kind of rubbery and stretchable. And again, we also, because of the microstructure, have something that is quite stable under a stretch, and so the resistance doesn't really increase. And so I'll just kind of briefly, and we've actually done extensive study on looking at these materials as bioelectronic interfaces. So EMG, EEG, ECG, interfacing with electronics, kind of surface mounted components to make these fully wireless and compatible with Bluetooth. So these are all things that we've kind of explored, and then what we found, I kind of will save you all the details. But in terms of the skin, basically the impedance matching matching with skin and the ability to kind of achieve high signal to noise ratios, these actually kind of perform on par, or actually in some cases outperform silver chloride gels and other kind of gold standards for bioelectronic interfaces. So here you have both a high electrical conductivity, but you also have this kind of soft rubber compliance that allows for really good interfacing with the body. And then, I'll just kind of, through the rest of this. I mean, these materials can also interface with liquid crystal elastomers, shape materials, and we can kind of start building kind of soft machines and other kind of interesting structures here. I don't want to spend too much time on this video on the bottom. It looks like it kind of having some issues too. It's a little bit choppy here, so I'm going to skip through that. But what I do want to mention before I kind of move on is that one of the areas that we're kind of looking at with these liquid metal silver flake biphasic architectures is now starting to think about not just achieving functionality for stretchable circuits, but also creating circuits and electronics that could be recyclable. The whole idea here is to really kind of scale things up to use these kind of in a in a very ubiquitous fashion, and more, especially when we kind of want commercialization of these technologies, there's a stronger emphasis on using materials that are more environmentally sustainable. So they're more eco-friendly, they can be recycled, or they can degrade. And so that's kind of where we're kind of headed right now. That actually just got accepted for publication, and hopefully within the next few weeks should come out. They basically have these electronics that are fully recyclable. And we can kind of use them in this kind of complete life cycle here. So I'll kind of also move, just in the interest of time, move through these slides a bit quickly, but just showing how we can use these kind of thin soft electronics to make smart tags to say track the temperature of food and monitor that over Bluetooth. And here are just kind of a few examples, and again, doing various types of bioelectronic sensing using these fully recyclable conductive inks. Here we're using a waterborne polyurethane elastomer as the matrix material. So something that's kind of well known within the paints community as kind of a more eco-friendly alternative to other solvent-based polyurethanes. And so it's something that we found actually is also quite compatible with these liquid metal-based systems. So the last set of topics here, I have about like 5 minutes or so to kind of wrap up, is to kind of now go beyond kind of these kind of rubber type matrix materials and start looking at hydrogels and organogels, because ultimately we want to use these materials for bioelectronic interfaces. We've had a lot of promising success with what I've shown you so far. But there's a reason that a lot of researchers prefer to use gels, right? I mean, these are much more biocompatible, not just in terms of cytotoxicity, but also in terms of the mechanical biocompatibility. Again, this came up this morning in Stephanie's talk, talking about, gels. And if you want to kind of interface with like brain tissue, for example, you really need to kind of take advantage of the really low mechanical stiffness, right? So we're not talking megapascals or hundreds of kilopascals in terms of Young's modulus, but we really want to get down to tens of kilopascals or even kilopascals of Young's modulus, for these applications, especially if we want to go even a step beyond just kind of on skin biointerfaces and start using these for implantable applications. And so that's kind of where we're headed. And again, we still want to maintain high electrical conductivity, and we want these materials also to be printable for kind of this large scale manufacturing. So hydrogels are, of course, great for this. I don't think I have to convince a lot of you of their kind of, use and future potential, especially kind of within, for implants and kind of biomedical type applications. When you think about, I say hydrogels, but, it's, we could also think about organogels. It really just depends on that solvent that you use. And so for the dispersion medium, if you're using water, there is that, concern, of course, that it can evaporate over time. We can actually take advantage of that. As I'll show you in a few slides, for some of our architectures. And then if you kind of switch to kind of an organic solvent like ethylene glycol, you can have gels that can resist evaporation even at elevated temperatures. So that's something also that we want to look at. As far as their kind of biocompatibility, so not only, again, do we have kind of mechanical biocompatibility, but, these are also safe, non-toxic materials. This is just a very recent paper that just got published. This is collaboration with Vicky Webster's Woods group. Sorry, the images, for whatever reason, I think this is a victim of the shift from Mac to PC, but the pictures here really got botched. So what the images in the top left are intended to show is that these biocompatible hydrogels, they're printable using this kind of direct inkwrite approach. We can create, again, sorry, the images got completely botched here, but you can kind of we can make these kind of soft machines, soft robotic grippers. What you really can't see here is the gripper kind of picking something up. And unfortunately, this is probably also going to get botched here too. So what we show here is actually a sea slug that can actually go and ingest our hydrogel soft robot. And again, the inset here got completely botched, but we can actually confirm that the sea slug basically just passes it through, and the basically all that hydrogel material just comes out as poop from the slug. So a bit anticlimactic from all the botched pictures here, but anyways, this is kind of not proof, but just consistent with kind of our understanding of these materials as being biocompatible and not really dangerous even to delicate organisms like a sea slug. All right, so kind of moving on. So how do we make these materials conductive? Well, of course, a lot of you who kind of have worked with these gels, know that, you can make ionic gels, right? Just depending on the type of solvent that you use, which is great for a lot of bioelectronic applications. But ionic gels don't have the conductivities needed for any kind of digital circuitry. And so what we wanted to was to make conductive gels that actually have electrical conductivity that could be used to kind of support any surface mount and kind of microelectronic components. And so for that, we just kind of took the naive approach of just filling it up with a high volume fraction of these silver flakes. And then what we did was take advantage of the fact that over time the water will evaporate. And as that happens, you basically start kind of removing some of the water between these silver flakes. You can actually form this kind of somewhat connected percolating network of silver flakes. And in this partially dehydrated state, you can get a hydrogel that has fairly high electrical conductivity, kind of, hundreds of Siemens per centimeter. So well, kind of within the range of what you need for digital electronics. And so I'll show you in the next video here, just using this for functional electrical stimulation. And even for an application like this, not only are we using it as the biointerface, but we're also using these materials as the leads. And so you can see that if this video runs, that you can use our conductive gel to stimulate muscle in a way that won't work with your more traditional ionic gel. So don't ask me how we got the IRB approval for this. I mean, it was just the student basically doing this test on himself. But you can see basically, even for this very simple application of just a wireless neuromuscular electrical stimulation, we're getting a very dramatic difference. And it really all just comes down to electrical conductivity. And then just kind of one other kind of fun feature of these systems is that, just as you can kind of partially dehydrate to achieve increased electrical conductivity, you can also rehydrate, and then you can basically break that percolating network, lose the conductivity. You can keep doing that again and again and again, and you can make these basically rewritable electrical circuits. So we kind of made this little robot here that kind of walks around with this, using this kind of simple kind of motor neuron type circuit where we kind of basically activate and deactivate the motor neurons by just using this hydration and dehydration. So in the video, hopefully you'll get a better sense of what I mean by this. And so this is in the partially dehydrated state. So both these are electrical conductive. So current is being delivered to both sides of the robot, to the motors. And now when we kind of rehydrate the left, you'll see we use a blue dye there just so you can see where we're kind of breaking up that network. You see now the motors on the left are a little bit slower, right? The reason this is significant is not just that we're showing this kind of programmability, but also the fact that the conductivity of this gel is so high, we can actually use it to deliver current to these motors. So again, this is also something that will just be infeasible with just ionically conductive gels. And then just to show you kind of in real world conditions too, you know, kind of in an ambient environment also, we can kind of get this effect here. So again, I'll just kind of skip through this just in the interest of time. I think you get the idea here. Yeah, here you can see it kind of biases a little bit to the left when we deactivate that neuron. All right, so the last kind of set of slides here is to show kind of, you know, where we really want to go with these, and that is to achieve kind of soft, conductive gel-like circuits with very low modules. And ideally, we'd like these to also be self-healing, right? Because the one danger of kind of making this transition to kind of from like flex or rigid PCBs to soft electronics is that soft materials are highly susceptible to damage, right? And you know, especially, you know, in kind of real world type conditions where they're going to be exposed to the same wear and tear as our natural tissue. And so as with natural tissue, we kind of want to have this kind of self-healing capability. Thankfully, when it comes to gels, there's been a tremendous amount of work by groups out there who have looked at kind of the self-healing properties of these gels. We are just simply adapting, you know, what's kind of been known for over a decade now about these material systems. And particularly, we kind of adopted a composition of borax, PVA, and also ethylene glycol as a solvent, and then we just kind of blend in the liquid metal and the silver. So I showed you before that silver alone is good for achieving high electrical conductivity. But if we want these now to be self-healing, we actually need the liquid metal in there. So when you can sever the material and bring it back in contact, the liquid metal can help aid in kind of wetting those silver flakes back together and restoring those percolating networks. So that's kind of what you're seeing here. So kind of in the pristine state, you have this kind of very stretchable type circuit. Again, we don't have to do any mechanical sintering on account of the presence of the silver flakes. And then because of liquid metal, when we cut these materials and then just bring them back together, they kind of spontaneously fuse. The PVA and borax, they kind of form the hydrogen bonds that are needed to kind of restore the mechanical integrity, and then you have the liquid metal to help kind of restore the electrical connectivity. And so here's just kind of technical feel for the material, so you mix it up. Step that I kind of left out here, kind of a cross-linking. We also do need an extra freezing step to help kind of increase the kind of elasticity of these composites. So without that extra freezing step, it still kind of is intact, but it's kind of has a very kind of viscous type property to it. So you'll see that in the next step here. Just kind of how basically it's self-sticky on account of that hydrogen bonding. Okay, so this is when we do cool it down, and you can see we can kind of tear it up. It sticks back together, so quite soft. And then depending on the freezing step, we can also make these to be quite elastic and rubbery. Here's kind of I'll just kind of end here with a fun demo, just showing using this again as a motor, quote motor neuron. I'm using that pretty loosely here, but just this is a fully wireless, untethered soft robot where we have control the battery, and then the motor is basically connected to the microcontroller through this kind of self-healing interconnect, right? When we cut it, you see the connectivity plummets, current basically decreases, motor slows down, and then when we kind of tamp on it, as you can see right there, that connectivity is restored and the motor starts speeding up again, right? So yeah, just kind of like a fun little demo. Just kind of shows that. I'll just play that one more time. The next set of demos really just kind of tie this into a more practical application, which is to use these for kind of self-healing or reconfigurable bioelectronic interfaces. And so, yeah, so there you can see again, we just kind of give it a little step in. You can see kind of the motor starts to slow down as the current decreases. This is all just a real-time video. So you can see it's almost pretty spontaneous, like restoring the electrical connectivity. We're kind of at time here, so I'm actually just going to Skip ahead here, but as you would expect, you can use these for EMG, ECG, various types of bioelectronic type applications. And then because of this kind of self-healing property, you can also get these to, let's see if I can, oh, I think I ruined it. All right, I'm not able to speed up here, but basically the next half of this just shows that you can take those two electrodes on the forearm and you can just basically stick them together and make a larger electrode and then place that on the calf, for example, and then you can do EMG on a larger muscle group. And then, of course, biocompatibility is, the other big issue. So we're not so concerned about the gels, but, anytime we have liquid metal, then there's the question of, okay, how safe is this? Is there concerns with cytotoxicity? So that's something that, we've had some promising results with C2, C12 mouse myoblast cells, but there's still a lot more work that we have to do to really confirm the biocompatibility of these systems. So I'll kind of wrap it up there. I think, I'm pretty much on time. So hopefully this time maybe for a question or two, but yeah, thanks so much.